Hello everyone, I am Priyam Mehta and this video is for my digital assignment in engineering physics. The topic that I've chosen is laser. I'll be covering the topics of basic introduction, laser characteristics, the working principle of a laser and the types of lasers. So laser, the word laser is actually an acronym. Let me minimize my window so I can view the presentation properly. So laser is actually an acronym. It stands for light amplification by stimulate emission of radiation. Lasers are devices that produce or amplify a beam of narrow, low divergence light with a well-defined wavelength within the optical region of the electromagnetic spectrum, covering the infrared, the visible, and the ultraviolet. Lasers have many applications. They're used in precision tools and can cut through diamonds or thick metals. They can also be designed to help in delicate surgeries. Lasers are used for recording and retrieving information. They're used in communications and in carrying TV and internet signals. We also find them in laser printers, barcode scanners, and DVD players. Lasers are also used in instruments called spectrometers. So basically, spectrometers can help scientists figure out what things are made up of. For example, the Curiosity rover, it uses a certain laser spectrometer to see what kind of chemicals are there in certain rocks on Mars. The basic principle of laser is based on the Einstein's theory of light proposed in 1916, which was later developed by Gordon Gould in 1957. In 1960, Theodor Maiman, he invented the first working ruby laser, which was also the first optical laser. Apart from solids such as ruby, researchers have analyzed that some material like xenon, helium, or semiconductors can also be used as laser mediums. Different types of lasers have since then been developed, which have enhanced the scope of their applications. So now laser has certain unique characteristics which makes it different from ordinary light. There are four such characteristics. There are directional, sorry, coherence, directionality, monochromacity, and high intensity. Let us discuss each of these in detail. Coherence. We all know that how visible light is emitted from the source. In an atom, when the electrons are excited, they jump from one state to another state or from higher state to ground state. And this is known as transition. In ordinary light sources, the electronic transition takes place randomly. And when the light waves are received from ordinary light source, the wavelength has no definite phase in space and time. These light waves are said to be as incoherent. In the case of laser light, the electronic transition takes place in an orderly way, and the wavelength has consistent phase with time, which is called as temporal coherence. Due to the characteristic of coherence, laser light produces large amount of power of the order of 10 power 13 watts and can be focused in narrow space of linear dimensions of 10 power minus 6 meters. Directionality. We must have observed how conventional sources emit light. The conventional source emits light in all directions, and this is known as divergence. For example, lamp torch light, sodium vapor lamp, etc. In the case of laser light, it emits light only in one direction, which is called as directionality of laser light. Suppose if the beam of light emitted from conventional source travels 2 kilometers, then it will also spread in the diameter of 2 kilometers. But in the case of laser, beam of light traveling to a distance of 1 or 2 kilometers will not spread more than a few centimeters. Thus, the property of directionality of laser helps to focus on the target at a large distance. Monochromacity. Monochromacity refers to a pure spectral color of a single wavelength. It means that light will be made up of only one color, having the same wavelength. Ordinary light is white light, which is the combination of all colors, which is observed when we pass it through a glass prism. But laser light is monochromatic. The range of frequency of wavelength of the maximum intensity is called bandwidth. The narrow bandwidth of laser light makes it highly monochromatic. Large amount of energy can be concentrated even in a small bandwidth due to the high monochromaticity of light. High intensity. This is another property of laser light. Intensity of a wave is defined as the energy per unit time flowing through a unit normal area. The ordinary light spreads uniformly in all directions and forms spherical wavefronts around it. Whereas in laser light, energy is concentrated in a small region of space with small wavelength but greater intensity. Now, since we understood these characteristics, to understand the working principle of laser, we need to understand a few concepts, namely absorption of radiation of light, spontaneous emission, and stimulated emission. So absorption. The process of absorbing energy from photons is called absorption of radiation. The electrons orbiting at a large distance from the nucleus have a higher energy level, whereas electrons orbiting at smaller distance from the nucleus have lower energy level. So as you can see in the diagram, let us consider that the energy level of ground state is E1 and the higher energy level is E2. When the ground state electrons absorb sufficient energy from photons, they jump into the next higher energy level of higher energy state. The absorbed energy should be equal to the energy difference between the two energy state, which is E2 minus E1. The electrons in the higher energy state are called excited electrons. The light or photon's energy applied to excite electron can be mathematically written as h nu equals E2 minus E1, where h is the Planck's constant, mu is the frequency of photon, E2 the higher energy level, E1 the lower energy level. Spontaneous emission. The process by which excited electrons emit The process by which excited electrons emit photons while falling to the ground level or lower energy level is called spontaneous emission. The electrons in the excited state do not stay for long period because the lifetime of electrons in higher energy level is very small, of the order 10 power minus 8 seconds. Thus, after a short period, they'll fall back to the ground state by releasing energy in the form of photons. The energy of the released photon is equal to the difference in energies between the two electron orbits. The electrons changing from one state to another state occur naturally. So the photon emission is also occurs naturally and or also known as spontaneous emission. The emitted photon does not flow exactly in the same direction of incident photon. They flow in random direction. This process is independent from outside circumstances. The light spreads in all directions around the source. Light intensity decreases rapidly with distance from the source, and the light is incoherent. Now let's understand stimulated emission. The process by which electrons in the excited state are stimulated to emit photons while falling to the ground state is called stimulated emission. So unlike spontaneous emission, in this process, light energy of the photon is supplied to the excited electrons instead of supplying energy to the ground state electrons. So this is an artificial process. The electrons in the excited state need not wait for natural spontaneous emission to occur. An alternative method is used to stimulate excited electrons to emit photons and fall back to ground state. The incident photon stimulates or forces the excited electron to emit a photon and fall into the lower state. The energy of the stimulating incident photon must be equal to the energy difference between the two electron shells. In this process, the excited electron releases an additional photon of same energy, same frequency, same phase, and in the same direction while falling to the ground state. So in stimulated emission process, each incident photon generates two photons. This is the only known method to produce coherent light. This process is controlled from the outside. The emitted photon has the same frequency, phase, and plane of polarization. The emitted photon propagates in the same direction as that of stimulating photon, and the light produced is monochromatic and coherent. Now, light amplification is a very important result of stimulated emissions. Let us understand the phenomena using the diagram. First, we supply a photon to the electron in an excited state. The electron is stimulated and thus moves to the ground state. It releases the energy in the form of a photon of the same frequency. Thus, now we have two photons. These photons can further stimulate two more electrons, and the process continues in exponential manner. Thus, by using one photon, we are able to cause stimulated emission in so many electrons. Population inversion. Population inversion is the state in which the number of atoms in higher energy state is more than those in lower energy state. Generally, a greater number of atoms are in lower energy state because they are more stable there. But in stimulated emission, we require more number of electrons in excited state. So we optically pump the atoms from the ground state to the higher state. The atoms quickly decay non-radioactively to a metastable state, which is a state with longer lifetime. Stimulated emissions happen between these metastable state and ground state. Pumping. So as mentioned before, to achieve population inversion, the atoms must be promoted or pumped from lower energy level to higher energy level. This process by which atoms are raised from lower level to higher energy level is called pumping. Pumping can be achieved in the following ways. Optical pumping. In this, light energy is used. The photons are made incident on the active medium. Flash discharge tubes, continuously operating lamps, spark gaps make use of this kind of optical pumping. Electrical pumping. Here, electrical current is passed through the active medium. Electrons collide with atoms and excite them to higher energy states. This method is used in gas lasers. Direct conversion. Electrical energy is directly converted into light energy. The electrical current is passed through active medium, but atoms are not excited. Sorry. But the atoms are not excited to higher states. The current carriers themselves are excited to higher states to achieve population inversion. Examples, semiconductor lasers. Now, since we understand the basic working principle of a laser, we can go forward and understand the types of laser classification. So lasers are classified into four types based on the type of medium used. These are solid state laser, gas laser, liquid laser, and semiconductor laser. Solid state laser. This laser uses solid as a laser medium. In these lasers, glass or crystalline materials are used. Materials such as sapphire, neodymium doped yttrium aluminum garnet or ND-YAG, neodymium doped glass, and yttrium doped glass are used as host material for laser medium. Out of this, ND-YAG is the most commonly used. The first solid state laser was ruby laser. It is still used in some applications. In this laser, a ruby crystal is used as a laser medium. Gas laser. A gas laser is a laser which has an electric current and discharged. An electric current is discharged through a gas inside the laser medium to produce laser light. In gas lasers, the laser medium is in the gaseous state. Gas lasers are used in applications that require laser light with very high beam quality and long coherence length. Liquid laser. A liquid laser is a laser that uses the liquid as laser medium. In liquid lasers, light supplies energy to the laser medium. A dye laser is an example of liquid laser. A dye laser is a laser that uses an organic dye as the laser medium. It is made up of organic dye mixed with a solvent. These lasers generate laser light from the excited energy states of organic dyes dissolved in liquid solvent. It produces laser light beam in the near ultraviolet to the near infrared region of the spectrum. Lastly, semiconductor laser. A semiconductor laser plays an important role in everyday life. These lasers are very cheap, compact size, and consume low power. Semiconductor lasers are also called laser diodes. They're very different from solid state lasers actually. In solid state lasers, light energy is used as the pump source, whereas in semiconductor laser, electrical energy is used as a pump source. Here, a PN junction of semiconductor diode forms the active medium of laser medium. The optical gain is produced within the semiconductor material. So that is the end of the video. Thank you.